Lesson 8.4, Telescoping Series. So similar to geometric series, a telescoping series is a type of series. But unlike geometric series, where the geometric series has a geometric series test, there is no telescoping series test. This is not technically a test. This is simply, if you see this type of series, use this particular technique to determine if it's convergent or divergent. Let's just start with an example. Consider we have the sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1. Now, of course, we should always start with the divergence test. And if we apply the divergence test, we should recognize that this one is going to be bottom heavy. So is this one. These are both bottom heavy. So if I take the limit to infinity, this would actually end up being 0 minus 0, which is 0. And by the divergence test, inconclusive. So the divergence test is not going to work on this particular series. Now, we could try asking ourselves, is this geometric? In which case, no, this is not geometric because it's not a number raised to a power. So then we jump to other techniques. Now, anytime you are in doubt of which test you should use, or you have no idea what to do, one thing you can always fall back on is simply expand out the series and see what happens. So in this case, let's do that. Let's just expand out the series and see what happens. If I plug in 1, I would end up getting 1 for the first term and 1/2 for the second term. Now also notice, because I am not going to go to infinity on this, I've labeled this sum, not the true sum, s, but s sub n, representing I'm going to go up to n terms. So I started with n equals 1. Now if I plug in n equals 2, I would get 1/2 minus 1/3. If I plug in n equals 3, n equals 4, n equals 5, and so on forever. It would just continue like this forever and always. Now again, as I said over here, I'm going to go up to the nth term. So that means this isn't an infinite sum. This is a finite sum. So the last term would technically be 1 over n minus 1 over n plus 1. And what I always like to do is not just to write the last term, I always like to back up one term before that. Now, if I were to back up one term before that, the term right before 1 over n would be 1 over n minus 1. The term right before 1 over n plus 1 would be 1 over n. Again, not a necessary step, it's just something I like to do just to illustrate what's happening here. So I've expanded out a bunch of terms, and now I'm going to explore what's happening. Now hopefully you should recognize something that happens immediately. 1/2 cancels, 1/3 cancels, 1/4 cancels, 1/5 cancels, and even though I didn't write the next term, I can predict that the 1/6 is going to cancel with the term that comes after it. And likewise, the 1 over n minus 1 is going to cancel with the term that came right before it. 1 over n cancels with 1 over n. So what happened here is almost every single term canceled, other than the first term, 1, and the last term, 1 over n plus 1. Everything canceled. And that's where the name telescoping comes from. Imagine one of them old-timey spyglasses that ye old pirate would have, where you have your poorly drawn version of a telescope, and you expand it out to use it, and then you collapse it down to stow it away. Well, that's exactly what happens to a telescoping series. A telescoping series is simply a series that telescopes. Telescopes, in other words, every term, all but a few finite terms cancel out. So in this case, the nth sum would be 1 minus 1 over n plus 1. Now, I'm not looking for the nth sum, I'm looking for the infinite sum. So let's just take the limit as n approaches infinity of that nth sum. Now, when I take that infinite limit, the 1 over n plus 1 goes to 0, and we're left with 1. Therefore, the sum of that series is 1, or it's convergent to 1. In general, any series of this form where I have a series minus another series can possibly be telescoping. We can't confirm that it's telescoping until we actually expand it out and see if it collapses. If it expands out and it doesn't collapse down to a finite number of terms, then it's not telescoping. So again, this is not a test per se, this is simply a possible technique. If it works, it works. If it doesn't work, try something else. Now, some generalizations we can make about telescoping series. Again, list out the terms to confirm that it's telescoping. Most of the terms should cancel, all but a few finite number of terms should cancel. And the sum is simply the limit as n approaches infinity of the remaining terms. So let's look at another example. Now your first thought on this one might be that this doesn't fit the same structure as we expected on a telescoping series, a sub n minus b sub n. So I look at this and say, well, this is clearly not telescoping, so let's try something else. I could try the divergence test. Notice that it's bottom heavy, so it goes to 0, divergence test fails. It's not geometric because it's not a number raised to a power. You might consider trying the integral test, but the problem is the integral test, I would need du over u, and if the bottom is u, n squared, the top would have to be du or n, and I'm not going to be able to integrate this. Until I think back, wait a second, I did something similar to this in the integration chapter, where I had a fraction that I didn't know how to integrate, but then I remembered, oh, you got it, partial fraction decomposition. So factor out the denominator, n plus 2 times n minus 1 breaks into two fractions, a over n plus 2 plus b over n minus 1, and then we can go through the process of partial fraction decomposition. I'm going to pause right here to give you an opportunity to figure out the a and the b value. Go ahead and pause the video, play when you're ready. So to figure out the a value, we're going to plug in -2 since that's what the a is on top of, and we'll cover up the n plus 2 in order to plug it in. So plugging in -2 for n, -2 minus 1 is going to give me -3, so the a value would be -1/3. Likewise, to figure out the b, we're going to plug in n equals 1. We're going to cover up the n minus 1 so that we don't get 0 on the bottom. Plugging in 1 plus 2, we get 1/3. So the a value is -1/3, the b value is +1/3. So rewriting the series as two separate fractions, I get this, but notice one of them is negative and one of them is positive. So what I can actually do is this. And now we have the structure needed for it to telescope. Again, I do not yet know whether this will indeed telescope, but at least it fits the structure of a telescoping series, some a sub n minus b sub n. Now, the other thing I notice, of course, is that both fractions have 1/3 in my numerator, and because remember, this is still a summation, and we have this factoring property that says if I have a common factor between terms that are being added or subtracted, I can factor it out. I'm just going to go ahead and factor that 1/3 up to the front, and then forget about it for now, and remember about it at the end of the problem. So what I'm going to do is I'm going to figure out the sum of just this part of the problem. So just this part of the problem, figure out that sum, and then at the end of the problem, if I do get a sum, just multiply it by 1/3 to get the true sum. So just like I did before, I'm going to expand out the terms. Notice this one starts at n equals 2. So when I plug in 2 minus 1, that's going to be 1 over 1 minus 1 over 4. There's my first term, my first pair of terms. Plugging in n equals 3, I get this guy, n equals 4, n equals 5, n equals 6, n equals 7, and so on and so forth. The last term would just be the original sequence itself, 1 over n minus 1 minus 1 over n plus 2. I like to, again, back up a term. In this case, I backed up n minus 1 becomes n minus 2, n plus 2 becomes n plus 1. And on this one, I went ahead and backed up a few more terms because I noticed that if I just do these two terms together, nothing's going to cancel. But if I back up another term and then another term, I notice right there that n minus 1 would actually cancel right there. So I always like to back up at least until something cancels on that last term. And let's see what happens. Now this one, notice it's not consecutive terms that cancel. It actually takes a while for terms to start canceling. The minus 1/4 will cancel right here. The minus 1/5 would cancel right here. The minus 1/6 would cancel right here. Now I don't see the 1/7 canceling, but I can predict that the next group of terms would begin with 1/7. So I know the 1/7 is going to cancel, the 1/8 is going to cancel, the 1/9 is going to cancel, and so on down the line. Now sometimes, again, it can be a little tricky to see exactly what's going to cancel here because not everything is actually canceling. Notice I kept the first term, the second term, the third term, and it wasn't until the fourth term that both pairs, that the entire pair of terms canceled out. So sometimes when it's a little trickier to see what the pattern is on how things are canceling, I like to go ahead and separate the positive terms from the negative terms. For instance, the positive terms would be 1, 1/2, 1/3, 1/4, 1/5, and so on. The negative terms start at 1/4, then 1/5, then 1/6, and so on. So if I do that, here would be the list of all the positive terms, again comparing that to the original, 1, 1/2, 1/3, all the way up to 1 over n minus 4, 1 over n minus 3, ending at 1 over n minus 1. And then the negative terms, again beginning at negative 1/4, then negative 1/5, all the way up to negative 1 over n plus 2, would be this. And notice what I've done here is I've lined them up so that clearly the 1/4 cancels, the 1/5 cancels, the 1/6 cancels, the 1/7, the 1/8, the 1/9 are all going to cancel. And likewise, the 1 over n minus 1 would cancel, n minus 2, n minus 3. Everything from here to here would end up canceling. By lining things up, I can see exactly what cancels and what does not cancel. Because the 1, the 1/2, the 1/3, the 1 over n, the 1 over n plus 1, and the 1 over n plus 2 don't cancel, and that's it. Now, I actually have a mistake here that I could fix and re-record, but I don't feel like it, so you get to see errors in practice. That ... should no longer be there because there are 1, 2, 3, 4, 5, 6, only 6 remaining terms. It should just strictly be 1 plus 1/2 plus 1/3 minus 1 over n minus 1 over n plus 2, 1 minus 1 over n plus 2. These are the only terms that remain. So then if I take the limit, the 1 over n, the 1 over n plus 1, and the 1 over n plus 2 are going to go to 0. So I'm just going to be left with 1 plus 1/2 plus 1/3. Those are the only terms that remain. So therefore, I'm convergent to 1/3 times 1 plus 1/2 plus 1/3. Because of course, remember, the true sum had that 1/3 out front, so let's not forget that that 1/3 is part of the answer. And then the 1 plus 1/2 plus 1/3 is the sum of the partial fraction decomposition part that we did. All right. And again, the question here is it convergent or divergent? So what this actually adds up to, not relevant. If you want to finish this and actually simplify it, it comes out to 11 over 18, but that's not really what the question is about. The question is about, does it add to a number or does it not add to a number? In this case, yes, it's convergent to whatever number that is, 11 over 18. All right, here's another one. Pause here. Go ahead and start this one off on your own. If you make it all the way to the end, fantastic. If not, hit play when you need. All right, so just like before, we're going to start by expanding out the terms. Starting at n equals 0, plug in 0, plug in 1, plug in 2, plug in 3, as many terms as you need to. So I went as far as plugging in 0, 1, 2, and then I'm going to stop when I get to the original sequence itself, arctan of n minus arctan of n plus 1. And then I'm going to back up a term, and I notice that this is going to cancel right here, so there's no need to go any further. This one is similar to that first example problem where consecutive terms are going to cancel. So I know this is going to cancel, this is going to cancel, so the only thing left is the first term and the last term. We're going to take the limit as n approaches infinity, and then I'm also going to have to remember a little bit of inverse trig. Now, inverse tan of 0 is asking at what angle is tangent equal to 0. Hopefully we remember that tangent of 0 is 0, so that's 0. And then inverse tangent as n approaches infinity, boy is it helpful if you remember your parent functions. Here is the graph of inverse tangent. So as we go to infinity, it's not increasing forever. It is bounded on the top by pi over 2, which means we are convergent to negative pi over 2, because of course 0 minus pi over 2 is negative pi over 2. And finally, the last question. Go ahead and take a moment, expand this out, see if you can figure this one out. Pause here, play when you're ready. All right, expanding it out, I get something that looks like this. If I plug in 1, I get n plus 7 minus n, 1 plus 6 is 7, so square root of 7 minus square root of 6 plus square root of 8 minus square root of 7 plus square root of 9 minus square root of 8, and so on. So this was n equals 1, n equals 2, n equals 3, n equals 4, all the way up to the last term, n plus 6, n plus 5. The one right before that would have been this guy, and then just for kicks I added one more term, although normally I would have just stopped right here because of course I see that n plus 5 is going to cancel with that n plus 5. Again, we have another weird one where it's not consecutive terms that cancel, but I can see, oh, square root of 7 is going to cancel, square root of 8 is going to cancel, square root of 9 is going to cancel, square root of 10 is eventually going to cancel with whatever's over here. And again, if it helps, try listing out your positive terms and your negative terms. For instance, positive terms would be square root of 7, 8, 9, 10, all the way up to n plus 6. Negative terms would be 6, 7, 8, 9, all the way up to n plus 5. And what you'd find is that you have an overlap between square root of 7 and n plus 5, where the remaining terms would actually end up being negative square root of 6 and n plus 6. Everything else would end up canceling out. Bloop, 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 bloop. And this one would end up canceling with something over here. All right. Take the limit to infinity. Negative square root of 6 is obviously just negative square root of 6. And then the square root of n plus 6, as n goes to infinity, that one is actually going to end up going to infinity. So here we have something that appears to be telescoping. It is telescoping, but just because it is telescoping does not make it convergent. It just means that I have a route to finding the answer. So I go through the process, it telescopes, it collapses, I plug in the limit, and I get divergent.